Hello, yeah. In this video, I will show you how to fit Poisson regression models in R. Actually, just very basic Poisson models. First, let's get a data set. As you know, there are many data sets built in R packages. There's a package called data sets. So load it in and get the data called walk breaks. This is the data set. Breaks is a counts. That's a dependent variable for Poisson regression, and Wu and tension are two factors, and that will be our independent variable. And the syntax for fitting Poisson regression is very easy, just using the R function GLM. Here, GLM stands for generalized linear models. You know that Poisson regression model is a special case of generalized linear models. And you know, general linear models use maximum likelihood estimation for parameter estimation. So that's why we will have likelihood function, and we'll have access to likelihood ratio tests and the AIC, all the good stuff. And those also are available in Poisson regression. So you can see the syntax is very simple here. Just a GLM breaks regress on tension plus Wu family to Poisson. So here I used the single quotes, but that's not necessary. I just type Poisson data for the data summary. You can see here this is a standard output from a Poisson regression model in R. The most important part is the coefficient table. You can see it listed there. Here, rules is a category variable with two categories, so there's only Wu B listed here. Tension may have three levels, so you get tension M, tension H listed here. So you got the p-values. These p-values are really from the World test comparing that category to the reference category. So for a multi-category categorical variable like tension, in the future, we'll do the type 3 analysis using the likelihood ratio test to see if overall, if this tension variable is significant. Okay. And another important piece of information, you can see the null deviance, the residual deviance, and the AIC value. Okay. So that's where you can actually grab the AIC value. As we know, a quick check for over dispersion is to look at the residual deviance over degree of freedom. If this ratio is far away from 1, then over dispersion will be a concern. Okay? So for this model, let's take a look. So this is 4.2, so that's a little bit far away from 1. So we think over dispersion is an issue here. And this is because in Poisson distribution, its variance equal to the mean. That's the famous property for the Poisson distribution. But this is also a limitation of the Poisson model because in many real-world situations, the variance will not equal to the mean. Okay. So when there is over dispersion, one quick fix is we can fit a called QuasiPoisson model. Okay. So what is a QuasiPoisson model? The QuasiPoisson model has the variance function equal to a constant times the mean. Okay. So for Poisson model, the variance equal to the mean, but QuasiPoisson, the variance equal to a constant times the mean, and that constant will be estimated from data. By adding that constant, hopefully we will, especially when it's bigger than 1, then we will address the over dispersion, to a certain degree. And the syntax for fitting QuasiPoisson is very easy. Everything is the same except family equal to QuasiPoisson. Okay, so M2 summary. And you can see these outputs from the QuasiPoisson model has everything as in the output for a Poisson model, except now the AIC is NA, it's not available. And this is unfortunate because when we use the QuasiPoisson model, we no longer have a likelihood function. It cannot be constructed. So we don't really have a likelihood function, so we cannot compute the AIC value. And there's something called the quasi-AIC value, co-AIC for quasi-Poisson models. They're a bit complicated. You have to use several other packages. So I just point out that they exist, but I'm not going to show you here. Okay, another thing I want to show you is how to fit a Poisson model with an offset term. Okay, and you know the offset term in a Poisson regression model usually is the duration of the exposure. So when we talk about Poisson for count data, the count is observed during a time period. So that the duration, the length of the observation period is the offset term. So I'll show you there how to put the offset term into a Poisson model. Actually, I'll do it two ways. First, let's get another data set. So I'm going to get to the library AER and get the ship accidents data. You can see this is the first few rows. So the incidence is the counts, and that's for a dependent variable. You get service, that's the, I don't know, number of days service. So that's our offset term, that's the exposure, right? Then you got type, construction, and operation. So let's take a look at the incidence. It has zeros. So if we want to take a natural log of number of years of service, then it cannot be zero. Okay, so what we do is now we're fitting a Poisson regression model on the subset of this data set, which is a service greater than zero. Okay, so here you can see the M3 is a Poisson model fitted with this syntax, and you can see after the formula there's a subset service greater than zero parenthesis. That is telling R fit the model using this subset with only those data points with service greater than zero. Okay. Then this is how you incorporate the offset term. So offset equal to log of service. Then family equal to Poisson, data equal to data. And here is the outputs. Okay. And there's another way you can incorporate the offset term. So here's the M4. You can see you can put the offset term in the formula. Okay, so here you can see the syntax. We have plus offset of natural log of service subsets family, and so that's the same. Okay, so here's the output, and this is identical to M3. Okay, I think that's all for this video. Hopefully you learned the basics for fitting a Poisson regression model.